You know, have you ever looked at some super complex piece of tech and just thought, how on earth do they even make that? Well, it's not magic. It's really just a recipe. And today, we're going to crack open that cookbook and learn the secret language engineers use to write it. Let's jump right in.
Think about something like the Tesla Powerwall. It's this incredible piece of engineering, right? But how do you actually go from just a pile of raw materials to this super sophisticated energy storage system? You need a blueprint. And that blueprint is written in a very specific language. And that's exactly what we're going to learn today.
Okay, so let's start with the absolute most fundamental idea here, the process. You can think of this as the engineer's master plan, the blueprint for turning, this into that.
Really, when you strip it all down, a process is just a fancy word for a recipe. You take your inputs, those are your ingredients, and you do a bunch of stuff to them, right? A series of operations to get your desired output, your final dish. Sounds simple enough, but believe me, the magic is all in the details.
Because in engineering, you just can't get away with a little bit of this or heat it up for a while. That just won't cut it. If you want to guarantee the exact same result every single time, you have to be incredibly precise. And that's where process variables come into play. They're basically the nouns and adjectives, the building blocks of this secret language.
So how does this whole language actually work? Well, just like any recipe, before you start cooking, you've got to understand your ingredients. What are they made of? And maybe more importantly, how do we measure them?
We're going to start with the absolute basics. You've got mass, which is really just how much stuff you have. Then there's volume, which is how much space that stuff takes up. And finally, density, which is simply mass divided by volume, tells you how packed in all that stuff is. These are like the very first words you learn in our engineering vocabulary.
Okay, now here's where the language starts to get a little more interesting. Some of these variables, like the mass and volume we just talked about, are what we call extensive properties. So think of it this way. If you have 2 glasses of water and you pour them into a bigger container, the total volume is just the volume of the first glass plus the volume of the second. It's additive. It makes sense, right? It depends on the extent or the amount of the stuff you're working with.
But then, on the flip side, you have what are called intensive properties. And these are totally different. They describe the state of the material, and it doesn't matter how much of it you have. For example, the density of water is the exact same whether you've got one single drop or the entire Pacific Ocean, and the same goes for its temperature.
So here's the key takeaway, the big difference. Extensive properties, they're additive. You can just add them up. But think about this. You can't take 2 cups of hot coffee, add their temperatures together, and get a super hot cup of coffee, right? It doesn't work that way. That's because intensive properties describe the state of the system, not its size. And believe me, that is an absolutely critical distinction for any engineer who's trying to control a process.
All right, so we've got a handle on our ingredients. We know how to describe them. Now it's time to get this assembly line rolling. How do we talk about our materials when they're not just sitting still, but they're actually flowing through the factory?
Well, for that, we use something called flow rate. The best way to think about it is like a river. You could stand on the bank and measure how much water, the volume, flows past you every second. Or you could measure how many kilograms of water, the mass, is flowing by. Either way, this one variable is what sets the whole pace for our entire process.
Okay, you ready for a little challenge? Let's see if you're with me. Imagine you've got some gas flowing down a pipe, and then all of a sudden that pipe gets way wider. So I want you to think about 3 key variables: mass flow rate, molar flux, and volumetric flow. What happens to each one of them? Go on, take a second to think about it.
Okay, you got your answer? First up, mass flow rate. The answer is, it stays exactly the same. This comes down to a fundamental law of physics, the conservation of mass. You can't just create or destroy stuff out of thin air. So if 1 kilogram of gas is going into that wide section every second, then 1 kilogram has to be coming out the other side every second. Simple as that. It has nowhere else to go.
All right, now what about molar flux? Now flux is just a way of saying flow rate per area. Since we already know the amount of gas flowing is staying the same, but the area of the pipe just got a whole lot bigger, the flux has to go down. This shows us something really important. The same number of molecules are still passing by, but now they're way more spread out.
Okay, so we've got our ingredients, and we've got them moving. But there's another piece to this puzzle. The environment they're moving through is just as important. The conditions inside our factory, they can literally make or break the final product. So let's talk about pressure. Imagine you're in a swimming pool. The pressure you feel at the bottom isn't just the air pressure on the surface, right?
No, you also have to add in the pressure from the entire weight of all that water pushing down on you. It's a pretty intuitive idea. The deeper you go, the more stuff is on top of you and the higher the pressure gets.
You know, when you check the pressure in your car's tires, what you're actually reading is something called gauge pressure. That's the pressure above the normal atmospheric pressure that's all around us. But engineers also use absolute pressure, which is totally different. That's measured from a perfect vacuum, from absolute zero pressure. And knowing the difference is absolutely crucial if you're working with, say, a vacuum chamber or a super high-pressure system where the air pressure around you is just a tiny fraction of the forces at play.
And of course, we can't forget the final big knob on our control panel, temperature. And it's so much more than just hot or cold. If you could zoom all the way down to the molecular level, temperature is literally a measure of how fast the molecules in a substance are zipping around and vibrating. It's a measure of pure kinetic energy.
Okay, we've learned the basic vocabulary: mass, flow, pressure, temperature. Now for the really cool part. Let's see how engineers take these simple words and combine them to write the recipes for some of the most advanced materials on the entire planet.
Let's take a look at maraging steel. This stuff is an incredibly strong alloy that's used in all sorts of high-performance applications. And its amazing strength? That's no accident. It is the direct result of a very specific recipe. You can see it's a super precise mix of iron, nickel, and cobalt. And if you change that recipe even a tiny bit, you completely lose the properties that make it so special.
So, using this language of process variables, engineers can actually calculate the alloy's average molecular weight right from its composition. Now, I know that number might sound super abstract, but it's like a vital fingerprint for the material. It's what allows engineers to predict exactly how that steel is going to behave under extreme stress. It lets them make sure that every single batch has that same exact superior strength.
And really, there you have it. This is the engineer's control panel. By precisely dialing in the what, that's the mass and composition, the how fast, that's the flow rate, and the under what conditions, pressure and temperature, engineers can design and control pretty much any manufacturing process you can imagine. So, whether we're talking about the electrolyte inside that Tesla battery we mentioned at the start, or the special steel in a high-tech flywheel, the underlying process is the same. It all comes down to mastering this handful of variables. This language, it's truly the foundation for, well, for everything we build in the modern world.
So there you go. Now you know the basics of this so-called secret language. So the next time you look at any manufactured object, you can start to ask yourself, what was the recipe for this? What variables did they have to control to make it? You now have the tools to start decoding the world around you. So my question for you is, what do you want to explore next?